For today's topic, we'll be looking at ammonia. We'll be looking at what are reversible reactions, manufacturing ammonia, which is also known as the Haber process, displacement of ammonia from its salt. First, let us look at reversible reactions. Many chemical reactions can only proceed in one direction only. These are called non-reversible reactions. Okay, they are not reversible. For example, potassium hydroxide reacts with sulfuric acid to form potassium sulfate and water. This is the reaction between your potassium hydroxide and sulfuric acid. Now, however, some reactions can be reversed. Some of the examples include the decomposition of hydrated copper to sulfate by heat. When blue crystals of hydrated copper to sulfate are heated, white solid of copper to sulfate are obtained at the end of the reaction. When water is added to the anhydrous copper to sulfate, the reverse reaction takes place. The white solid of copper to sulfate will react with the water to form back your hydrated copper to sulfate. Okay, so here we have your blue crystals of hydrated copper to sulfate, and the water is removed by heating. Okay, so you will obtain your white powder of your copper to sulfate over here. So when the white powder of your anhydrous copper to sulfate reacts with water, it will form back your hydrated copper to sulfate. This is a reversible reaction, and the equation can be written as below. Pay attention to the arrow used in the writing of the equation. Let us look at another example. Your solid ammonium chloride decomposes upon heating to form your ammonia gas and hydrogen chloride gas according to the following reaction. Now upon cooling, your solid ammonium chloride reforms. This is another example of a reversible reaction. We say that a reversible reaction can go both forward and backward at the same time. A double arrow sign is used to indicate a reversible reaction. So for the previous example, you have your ammonium chloride reacting to form your ammonia gas, as well as your hydrogen chloride gas. Now since this is a reversible reaction, we use this double arrow sign to indicate that this is a reversible reaction. The reaction from the left to the right is called the forward reaction. In this case, it is the reaction of your ammonium chloride to form your ammonia and your hydrogen chloride gas. Now, the reaction from the right to the left is called the backward reaction. Many reversible reactions do not go into completion. Let us look at the reaction between your sulfur dioxide with oxygen. There will still be some sulfur dioxide left over at the end of the reaction. If we carry out the reaction at about 450 degrees Celsius, about 2% of the sulfur dioxide will remain. When no more sulfur trioxide is produced, we say that equilibrium has been reached. Equilibrium is achieved when the amount of your reactants and your products no longer change. The amount of reactants and products at equilibrium can be altered by changing the different reaction conditions. For example, your temperature or the pressure at which the reactions are actually being carried out. Now, pause this video and take a few minutes to complete the following question. Check your answers. Do take note that since this is a reversible reaction, you will need to use a double arrow to write the chemical equation for this reaction. Now, let us look at ammonia and its different uses. Ammonia is used in the production of fertilizer and hence of food. It's also used in the manufacture of many different chemicals such as your nitric acid, your nylon, your dyes, cleaners, as well as chemicals for your electric cells. Ammonia is produced from your nitrogen, and of course in this chapter we will study the manufacture of ammonia and some ammonium salts. Now, the pie chart over here shows us a breakdown of the different uses for your ammonia. Now, after looking at the reversible reaction as well as what are some of the uses of ammonia, we will now be looking at the more important part of the chapter, which is the manufacture of ammonia itself. This process is also known as the Haber process. Now, the equation for the reaction of the Haber process is as follows. Again, notice that there is a double arrow sign that is used in the chemical equation for the reaction of the Haber process. This tells us that the reaction is actually a reversible reaction. Now, the raw materials for the Haber process, they are nitrogen and hydrogen. Nitrogen that is used in the Haber process is extracted from the fractional distillation of liquid air, whereas your hydrogen that is used in the Haber process, they are produced from the cracking of your petroleum or the electrolysis of water. As nitrogen is an unreactive element, there is no reaction at all between nitrogen and hydrogen at room temperature. A high pressure and a relatively high temperature are needed for the reaction to occur. Now, for the forward reaction, we have your nitrogen reacting with your hydrogen to form your ammonia gas. As this is a reversible reaction, we will also have your backward reaction occurring at the same time, which is your ammonia breaking down to form your nitrogen gas and hydrogen gas. The overall equation for the reversible reaction between your nitrogen and your hydrogen to form your ammonium gas is as shown. Next, let us take a look at the effect of temperature on the reaction. What you are seeing here is the equilibrium percentage of ammonia that is formed from the reaction on the y-axis of the graph. Now, at a different temperature, you actually notice that the equilibrium percentage of ammonia that is formed from the reaction, they are actually different. From the graph, it is noted that a low temperature will reduce the decomposition of ammonia back to your hydrogen and nitrogen. This will increase the yield of your ammonia from the reaction. However, having the reaction take place at a low temperature will make the reaction proceed very slowly. Next, let's take a look at the effect of pressure on the reaction. Now, looking at the same graph, you can see again, when different pressure is used, the equilibrium percentage of your ammonia that is obtained differs. From the graph, it is noted that the yield of your ammonia is increased by using high pressure. But maintaining high pressure is costly, as expensive equipment like special pumps and stronger pipes, they are needed. There is also a safety risk involved in carrying out the reaction at a very high pressure. Last but not least, let us take a look at the effect of catalyst on the reaction itself. Now, we know that a catalyst is used to speed up the reaction. The best condition for achieving the maximum yield of your ammonia in your Haber process is as follows. Firstly, the temperature is set at 450 degrees Celsius, pressure at 250 atm or atmosphere, and finely divided ion catalyst is present during the reaction to speed up the reaction itself. This slide shows you the overview of the industrial manufacture of ammonia in a factory. Firstly, you have your nitrogen, okay, 1 volume from your fractional distillation of liquid air. You have your hydrogen, 3 volumes from cracking of your petroleum. Your nitrogen and your hydrogen, they are mixed in a proportion of 1:3 by volume. Okay, this is reflected in your chemical equation, okay, between the reaction between your nitrogen as well as your hydrogen to form your ammonia. The mixture of gases is then compressed to 250 atm or atmosphere. The gases are heated to 450 degrees Celsius and pass over finely divided iron. The reaction is exothermic, and only about 10 to 15% of the nitrogen and hydrogen is converted to ammonia. Next, a mixture of ammonia and the unreacted nitrogen and hydrogen is obtained. The mixture of gases that is obtained is then cooled, and ammonia gas condenses to form your liquid ammonia and is collected. The unreacted nitrogen and hydrogen gas are then recycled and are pumped back into the converter for future reactions. To summarize, these are the conditions required for the manufacturing of ammonia. You have your raw materials, your nitrogen and hydrogen. Nitrogen is obtained from the fractional distillation of liquid air. Your hydrogen produced from the cracking of petroleum. Conditions: high pressure and a relatively high temperature is needed, and iron is used to speed up the reaction. Finally, this is the word equation for the Haber process. Your nitrogen reacting with your hydrogen with finely divided iron as your catalyst to form your ammonia gas. For the last part of the chapter, we'll be looking at the displacement of ammonia from its salt. Recall from the chapter on your acids and bases. When an ammonium salt is heated with an alkali, for example your sodium hydroxide, ammonia is displaced from the salt. For example, when ammonium nitrate reacts with your calcium hydroxide, ammonia gas, your calcium nitrate, and water is produced. Another example is the reaction between your ammonium chloride and your sodium hydroxide. In this case, your ammonium gas, sodium chloride, and water is produced. The general equation for the reaction between an ammonium salt and an alkali is as shown. Loss of nitrogen from fertilizers. Sometimes, agricultural land becomes too acidic for good growth of food crops due to acid rain and excess use of fertilizers by farmers. Farmers will then neutralize the acidity by adding alkali to the soil. Calcium hydroxide and calcium oxide, or quicklime, are widely used in agriculture to neutralize excess acidity in soil. However, both your calcium hydroxide and your calcium oxide will react with nitrogenous fertilizers to form your ammonia gas. This causes the loss of nitrogen from fertilizers already added to the soil by farmers. Thus, nitrogenous fertilizers and lime should not be added to the soil at the same time. For example, we have the ammonium chloride fertilizer, and if let's say the farmer adds your calcium hydroxide to the soil, your ammonium chloride will react with the calcium hydroxide as added to produce ammonium gas, calcium chloride, and water. So as you can see from the reaction, the production of your ammonium gas over here will result in the loss of nitrogen from the fertilizers and the soil. Hence, like what was mentioned earlier, this causes the loss of ammonia and nitrogen from the soil. Thus, farmer must be careful not to add your calcium hydroxide and ammonium fertilizers to the soil at the same time.